very good morning, students. In the previous lectures we have been discussing about the construction of embankments either on soft clay soils or very steep embankments on a hard foundation soil. And in this lecture let us look at the topic of the use of geosynthetics for accelerating the pre-consolidation of the soils. And the brief outline of this lecture is we have already seen that any construction on soft clays we have to deal with very low bearing capacities and very large settlements and large lateral flows, and potentially any engineering construction on the soft clays will have to deal with this before we take up any construction. And traditionally the accelerated pre-consolidation is a conventional solution that is used for addressing this problem, and we use it not only to increase the strength of the foundation soil, but also to reduce the potential settlements after the construction work is completed. And the use of geosynthetics has improved these techniques a lot. And some of the techniques that we can use for accelerating the pre-consolidation of the clay soils are the sand drains. Historically the sand drains have been in use for a very long time, right from 1920s up to probably mid 70s. After that we have the prefabricated vertical drains made of geosynthetics, and then more recently the vacuum assisted pre-consolidation. And the approach that we take for accelerating the consolidation is the reducing the flow path. Here we see an illustration of the construction of an embankment on a soft clay of certain thickness, and if it has to consolidate under the applied load, the water particle has to travel all the way from this depth up to the surface. Whereas if we install very large number of highly permeable sand columns, which are known as sand drains, schematically they are illustrated here, the maximum length a water particle has to travel to escape from the soft clays is only this much. And we already know that our time for consolidation is directly proportional to the square of the drainage path length, as illustrated here. The TV is the time factor that is related to the coefficient of consolidation CV, the time t, and d square. D is the drainage path length, and if we did not have the sand columns, the water particle has to travel this much distance, whereas if we install the sand columns, the water particle has to travel only this much. So you can imagine by how much the time for consolidation will reduce. And in all these cases, when the water comes out, we need to have a mechanism for leading the water away from the construction site, and that we achieve by providing a sand blanket like this. And these sand drains or sand columns are typically 200 to 600 millimeters in diameter, and the empirical experience has shown that the sand in the sand drains should be at least 1000 times more permeable than the native foundation soil. And to achieve very high permeability, we require the sand that is placed in the sand drains to meet a certain gradation requirements. And one of the earliest to recommend this type of recommendations is the California Department of Transport. In fact, that is where the first application of the sand drains has taken place. It is mostly it is coarse grained soils. We see that more than 50% of the soil is coarser than number 30 US sieve, that is approximately 600 microns. And as the water is coming up through the sand drains, it should be able to flow away from the construction site, otherwise it will percolate down into the ground. And the blanket soil, for that reason the blanket soil should be more permeable than the sand drain soil to drain away the water coming from the ground. And the usual thickness, we need to design the thickness so that there is adequate flow path for the amount of water that is coming out to drain out. And as we can see, more than 80% of the soil that is placed in the blanket should be coarser than 600 microns. In the previous case, 50% was coarser than 600 microns, whereas here more than 80% should be coarser than 600 microns, because this soil should cater to the quantity of water that is coming out from the ground. And the design of the sand drains is based on certain principles, and the governing equation is the 3-dimensional consolidation equation, where u is the pore pressure, x and y they are the horizontal dimensions, x and then z is the vertical dimension, and the ch is the coefficient of consolidation in the horizontal direction, and Cv is the coefficient of consolidation in the vertical direction, and T is the time. And the solution for this is derived by several people, notably the Richard and others, and Carrillo in 1942 he has proposed this solution that combines the effect of the vertical drainage and also the radial drainage in this form. He proposed that the average degree of consolidation that we can achieve because of the combined radial and vertical drainage can be written as 1 minus uv times 1 minus ur, where u is the degree of consolidation varying from 0 to 1. And the principle for designing is, in a given time, in a certain time, we would like to achieve, let us say 90% of the consolidation, and so we need to design the spacing so that this net sum total of the consolidation that we can achieve because of the combined consolidation is so much. And the solution for the consolidation due to vertical drainage is given way back in 1943 by Terzaghi, and he has also proposed these empirical equations. There are several such equations, and one set of equations that works out very well is this, wherein the time factor is related to the degree of consolidation as pi by 4 times u square, where u is less than 53%, and if the degree of consolidation is more than 53%, the time factor is related to degree of consolidation through this equation. So, for any given time factor, we can find the degree of consolidation, and the radial consolidation theory has been solved by several researchers, and Barron in 1952 he has proposed solutions for two types of field analysis. One is the free strain case, wherein we apply flexible loading and the settlement is non-uniform, and the other theory is equal strain theory or the rigid loading, wherein our settlements are equal all through, and invariably the equal strain theory is more applicable because our foundation structures they tend to be rigid. And here he has the final solution that was proposed by Barron is like this: the degree of consolidation in the radial direction is 1 minus exponent minus 8 Tr by function, which is written in terms of n, where this function f of n is written as this: n square by n square minus 1 ln of n minus 3 n square minus 1 by 4 n square, and our Tr is the time factor for radial consolidation, that is equal to Cr T by dE square, where Cr is the the coefficient of consolidation in the horizontal direction, and because in the radial consolidation equation is solved in the radial coordinates, instead of writing this coefficient of consolidation as CH, we write it as CR T by dE square, and our N is RE by RW, where RE is the radius of the unit cell area. We assume in all these analyses that each sand grain influences certain area of soil all around, and that area is converted into an equivalent circle, and this RE is the radius of that unit cell area influenced by each of the sand grains, and that depends on the pattern of installation. There are different patterns, that is one is a square pattern wherein along length and width the sand columns are installed at equal spacings, and the other is a triangular pattern that we will see a bit later on, and RW is the radius of the sand grain, and dE is the diameter of this unit cell area that is influenced by each of these sand columns. Our radial consolidation is very fast because of two reasons. One is because of higher permeability in the horizontal direction. We all know that most of the clay soils, they are highly anisotropic and they have different properties in different directions, and because their direction of deposition is in the vertical direction, they have an easy flow path in the horizontal direction as compared to the vertical direction. So, they have a higher permeability, and relatively that gets reflected in higher coefficient of consolidation, and of course the shorter drainage path. Because of these two reasons, our consolidation, radial consolidation is very fast, because in a given time if we are able to achieve about 10% degree of consolidation in the vertical direction, the degree of consolidation that is achieved in the radial direction could be of the order of 80 to 90%. And for a very long time the sand drains have been very popular for treating the soft clay soils, but then there were many instances where the sand drain treatment did not help in accelerating the pre-consolidation settlements, and some of the problems that were encountered are as follows. The sand within the drains gets clogged easily, because the soft clay is may have very fine particles, and in due course the fine soil particles come into the sand and clog the openings, thereby impairing the permeability of the sand, and then the continuous drainage path may be disturbed because of internal shear deformations, because all these the pre-consolidations are achieved by constructing a surcharge, and if we are not careful enough in applying a uniform pressure and applying the surcharge load at a slow enough rate, there could be large lateral deformations or the shear deformations, and because of these shear deformations the sand columns may undergo some distortion, and in that case the flow path is disturbed, and once the flow path is disturbed, that particular sand column becomes ineffective, it cannot transmit any water, and it takes a very long time to install the sand drains, because we need to first drill a borehole of certain diameter, like say 200 or some diameter as per our designs, up to the bottom of the soft clay layer, and then we have to fill that with sand of a certain gradation, and because of the complicated installation process, there are many cases where the flow path is disturbed because of the smearing of the clay soil all around. It is basically remolding of the clay around that reduces the drainage capacity of the sand drains, and because of all these reasons there is a need to come out with better methods for accelerating the consolidation, and the the introduction of the geosynthetics has helped in completely transforming the way we look at this problem of the pre-consolidation. And here we see an example of a soil embankment that is placed to drive the consolidation, and we all know that unless there is an increase in the effective stress, the consolidation will not happen, and the increase in the effective stress is achieved only by increasing the total stress. And initially, as per the Terzaghi's theory, we know that initially all the total stress is taken by pore water, and so the pore water pressure is equal to the total stress, but as the time passes by, because of the drainage of the water, gradually the pore pressure reduces, that in turn increases the effective stresses, and the increase in the effective stress is the one that causes compressions, and once the soil compresses, the void ratio reduces, and the clay soil particles are tightly packed, and because of other reasons like the secondary van der Waals forces and others, the strength of the soil increases. So, that is the basic principle of the pre-consolidation that we have, and because of all the problems that we can potentially have with the sand drains, once the geosynthetics have come into the market, a very large number of varieties of geosynthetics have been manufactured just for the purpose of pre-consolidation. And here we see the cross section of a typical PVD. This is the prefabricated vertical drain, or it is also called as a wick drain. In the case of the sand drains, because of the pressure applied, that provides the gradient for the water to flow, and the water flows through this wick, and this as opposed to the sand drains, this has two components. One is a drainage component and the other is a filter component, whereas in the case of sand drains, there is only drainage component, there is no filter to stop the fine soil particles from migrating and then clogging the sand. Here we have the different types of drainage cores. The one simple thing is a corrugated plastic sheet, and we can have a woven or a non-woven geotextile cover that acts like a filter, and the purpose of the filter is only to filter out the fine soil particles from escaping from the foundation soil. And typical properties of the PVDs, typically they are about 100 millimeters wide and 5 millimeters thick, and the inside core could be made of corrugated plastic sheet, or we can make the inside core using geonets or some other materials like the crimped wire mesh and so on. And the tensile strength of each of these PVDs is about 5 to 15 kilonewtons, because they are made of very good quality geotextile, and because of that they could have very good strength. And typical discharge rate that is measured as per the ASTM D4716 is anywhere from 2 to 5 liters per minute, so which is quite substantial. And as I already mentioned, these PVDs, they consist of a drainage core and a filter cover all around, and main advantage of these PVDs is they come in large roll lengths of about 100 meters or more, and these can be pushed rapidly into the ground to desired depth, because that is where the major difference between the sand drains and the PVDs come in. For the installation of sand drains, we need to drill a borehole and then fill it with sand of required gradation, and also when we fill the sand, it should be compacted and so that the borehole does not collapse. Whereas here in this case, we take a prefabricated drain that already comes in rolls, we just simply push it into the ground, and the type of soils that we deal with are extremely soft, that may have a cohesion of about 5 to 10 kPa, or at the most about 25 kPa, and it is very easy to push them. And here we see an example of the PVD that is coming in a roll, and we are this PVD is being connected to an anchor plate that gets that is connected to this rod, and it just simply pushes the anchor plate, and along with the anchor plate the PVD enters the ground. And here we can see some PVDs that are already installed, and the entire field is a soft clay soil. And here we see another view of the same thing. We see number of these PVD rolls here, and another close up of the same thing is actually we take the PVD from this roll and feed it into this rig and connect it to the anchor plate. And here another close up, and we can see this crawler mounted. Like most of these PVD rigs, they are lightweight compared to the other equipments. These come in on crawlers, and it is easy to move them even on soft clays. And yeah, here we see the entire view with the entire boom, and the PVD is installed by just simply pushing. And in some cases, if we are not able to push, we also use the water jet to assist in the installation. And typically to install a PVD of about 10 to 15 meters, it takes hardly 3 to 4 minutes. Compared to that, the installation of sand drains takes a long time, because we need to position the drilling rig at the location, and then connect all the bore rods, and then drill a hole, and then stabilize it with either a casing pipe or bentonite, and then later fill that borehole with sand. And these are the different types of connector plates for connecting the PVD, and these connector plates are the ones that are rigid and they can be pushed, because the PVDs themselves are highly flexible and they cannot be directly pushed into the soil. And this particular picture is taken from Koerner's textbook on the geosynthetics. And here we see a picture of the PVD being manufactured. These are all the the plastic cores that are put inside the PVD, and they are all joined together by welding process, by heat bonding, and then these plastic cores are covered with a geotextile. In this particular case, it is a woven geotextile. And here we see the view of the site that is treated with prefabricated vertical drains. We have number of these, and after the PVDs are installed, we need to lay the blanket soil that is highly permeable, so that all the water that comes out can travel away from the construction site. And some of the advantages that are claimed for prefabricated vertical drains are like this. The continuous flow path is ensured even after shear deformations, because these PVDs are highly flexible. They can be bent or they can be twisted without rupturing, because both the core and the cover, that is the filter, are highly flexible, and they can be strained up to about 20% without rupturing. So, because of that, even if there is some internal deformations or internal shear deformations, the PVD will only elongate or twist without rupturing, and because of that the continuous flow path is ensured. And the ASTM 4716 code for testing of the PVDs also has a provision that these permeability tests, they should be done at a very high pressure, and also by simulating the kinking. The kinking is the bending of the PVD because of internal deformations, and these discharge rates are the worst case discharge rates under very high pressure and with some amount of kinking. So, because of all these reasons, the flow through the PVD does not stop even if there is some deformation in the ground, and because we have a geotextile filter, there will not be clogging. That means that we have to properly select the geotextile cover based on the in situ soil properties, based on the grain size distribution and other things. That is all the principles that we have for the design of filters are applicable in this case. And because each of these PVDs they have some tensile strength, they also give some reinforcement action because of the tensile strength of individual PVD, because typically these are installed at a spacing of about 1 to 3 meters center to center, and so we can expect very large number of these PVDs within a unit area that can provide some tensile resistance either from lateral deformations or from horizontal deformations. And the typical arrangements, either PVD or sand columns, are like this. One arrangement is a very simple square pattern, wherein along the length and width of the site we place these PVDs at equal spacing S in this direction and also the same S in this direction, and the area of the soil that is influenced by each of these PVDs is assumed as a square, and for the purpose of our mathematical analysis we convert the square into a circular shape, because then we can just work with polar coordinates and solve the equations easily, and this we call as a unit cell. And if small d is the diameter of the sand drain or the PVD, and if capital D is the diameter of this unit cell, the factor n that we have seen earlier is basically the capital D divided by the small d, and if S is the spacing, the influence radius, that is radius of the influence zone in the square pattern, is 1.128 times S. And another popular pattern is the triangular pattern, wherein there is equal spacing, but in a triangular manner, like diagonally the spacing is equal, but not the other way. And the triangular pattern has the advantage that the circle fits better within this hexagonal shape, and because of that the influence areas from one sand drain does not influence the soil from the other sand drain, and so there is a better coverage, and the influence radius in this case is 1.05 times the spacing S. And it is found that the triangular pattern is more efficient, because when we draw a number of these circles, the area of the soil that is not covered by any of the sand drains, like for example in this area, in this square pattern, this area of soil is not covered, and as the spacing is increasing, that uncovered area of the soil becomes substantial, and that part of the soil may not consolidate, whereas the other rest of the soil may consolidate. And the design of PVDs, it can be done in the same manner as the sand drains, but in 1979 one Swedish engineer by name Hans Boe, he has presented some data from large number of field tests that he has carried out, and he related the time for consolidation T in terms of the influence diameter D, capital D, and CH, that is the coefficient of consolidation in the horizontal or radial direction, in this manner. the d square by 8 CH ln capital D by small d divided by 1 minus small d by capital D square minus 3 minus d by d square by 4 ln 1 by 1 minus u bar, and in this equation we can neglect this d by the small d by capital D, because invariably this is very small, because the small d is of the order of let us say 0.1 or 0.05, whereas capital D is of the order of 1 to 2, and the square of that is even smaller. So, by neglecting this term, the small d by capital D term, we can simplify this equation like this. The time for consolidation T is capital D square by 8 CH multiplied by ln capital D by small d minus 0.75 multiplied by ln 1 by 1 minus u bar, wherein our CH is the coefficient of consolidation in the horizontal direction, and the small d is the equivalent diameter of the PVD, and capital D is the diameter of the influence area of the soil, and u bar is the average degree of consolidation that we desire within a time of small t. And it is very simple to solve this equation by trial and error, and you can see that the contribution of the vertical drainage is neglected in this equation. What Hansbohr said is most of the consolidation is happening because of the radial drainage, and because of that it is reasonable to neglect the contribution of the vertical drainage, because anyway it is very small. And let us look at a small numerical example on the design of the spacing of the PVDs for achieving pre-consolidation. Let us say that we have a PVD having dimensions of 100 mm width and 5 mm thickness, and we would like to achieve 80% consolidation in 1 year time, and the coefficient of consolidation CH is given as 10 meter square per year. And the first thing is because our PVD is a rectangular in shape, we need to convert to equivalent circle, because all our solutions are given only for radial geometry or the polar coordinates. So, our pi d, if d is the equivalent diameter of the PVD, pi d is the circumference of the PVD, that is 2 times 100 plus 5, that is the circumference, and so this equivalent diameter is 66.8 millimeters or 0.0668 meters, and the equation that we have is in terms of the time for consolidation T as all this quantity capital D square by 8 CH and so on, and so the time is 1 year, and D is the one that we need to find, and 10 is the coefficient of consolidation in horizontal direction, that is 10 meter square per year, and the u bar, that is the desired degree of consolidation that we want to achieve, is 0.8. So, this if we simplify and take this 8 times 10 and this ln of 1 by 1 minus 0.8 to the left hand side, this is 47.706 is capital D square multiplied by ln D by 0.0668 minus 0.775, and we can solve it by trial and error. By substituting different D's, we can find the right hand side quantity, and when the right hand side quantity is approximately equal to the left hand side quantity, we can stop the iterations. So, if we start with a D of 2, it comes out as 10.59, with 4 it comes to 53.46. So, that means that the capital D is in between the 2 and 4, because at 2 the right hand side is less than 47, and at 4 the right hand side is greater than 47. So, let us try 3.5, it is it's about 40, and let us increase it to about 3.85. Actually there are several trials that were made, but all of them were not listed here, and finally at a capital D of 3.85, the right hand side is 48.96, which is very close to 47.7. So, it is so we can say that the diameter of the influence area D should be 3.85 to achieve 80% consolidation within 1 year time using this particular PVDs. And here is actually there is this equation is taken, and for different potential wick drain spacings, what is the time that we can that we require to achieve different degrees of consolidation. Let us say this is our 80% consolidation is our interest. So, this is the line that shows the degree of consolidation, and we can say that within 1 year, that is about 365 days, is about 3.85. is actually you can, if you do not want to solve it by trial and error, you can just go on substituting different capital D values, plot a graph, and between the horizontal the center to center spacing on the horizontal axis, and on the vertical axis the time for consolidation, and we can read it off, and in this case both of them they give 3.85 spacing. And if we want higher degree of consolidation 90%, the time the spacing is lower, and if we want within 1 year, if we want a lesser degree of consolidation, we can have a higher spacing as indicated here. After we determine the diameter of the unit cell area, now we can determine the spacing in the square and triangular patterns. In the square pattern, the spacing is 3.4 meters, and in the triangular pattern the spacing comes out as 3.66 meters, and between these two we prefer triangular pattern because the spacing is larger and also the coverage is much better. So, we get better efficiency by using a triangular pattern. And is there a way of achieving even faster consolidation than PVDs and not using a surcharge, and that is possible by using a vacuum for driving our consolidation. And the principle is very simple. We remove the atmospheric pressure from the volume of clay that needs to be consolidated, and then the atmospheric pressure itself acts like the surcharge, and then it drives the consolidation. And as you know, the vacuum is an isotropic stress or an isotropic pressure. So, we get much better consolidation with vacuum treatment. And typically there are two types of field installation methods. One is a membrane system, that is that was developed first when the vacuum techniques have come into the market. Here we cover the entire volume of soil to be treated by using a geomembrane, and we use a bentonite filled trench all around the treated area to isolate the volume of soil that is treated from the rest of the soil medium, so that our vacuum is preserved. And this method was developed by Maynard Soil Treatment Company in France. And there is another system called membraneless system, wherein the vacuum pipes are directly connected to the PVDs without any membrane, and this is called as a Bew-Drain method that is developed in the Netherlands. And the membraneless system is suitable for sites where we have a thin layer of hard clay that is relatively impermeable, and it will not allow the vacuum to be leaked. And both of them can be illustrated. I will show you the pictures later. Some of the pre-consolidation by vacuum are like this. The PVDs or the perforated pipes are installed vertically at 1 to 3 meters center to center spacing, and initially when the technique came in, the companies have used perforated vertical pipes to suck the water or to apply to distribute the vacuum into the soil. But later on, once the PVDs have come into the market, PVDs are used to distribute the vacuum, and these are installed at spacings of 1 to 3 meters center to center spacing. And these vertical pipes, they are connected to the horizontal drain pipes at the ground level, and typically we need about 14 horsepower vacuum pump for treating an area of soil equivalent about 600 to 900 square meters plan area, and we can treat the soft clay soils as deep as 20 meters, and typically 90% consolidation can be achieved within 2 to 3 months. And one main advantage of the vacuum treatment is we can get rid of even the secondary compressions that is not possible with ordinary surcharge method. Schematically, the system that employs a geomembrane cover is shown here. We have number of these PVDs or perforated drain pipes that are connected to horizontal pipeline that is connected to a vacuum pump, and we cover the entire area by a membrane, and once we create a vacuum here, the atmospheric pressure directly acts on it and to drive the consolidation. So, here the main principle that we have is we increase the effective stress without increasing the total stress. That is the main principle that we will see later on, and the vacuum pressure is isotropic, that is it is equal in all the directions, in all the radial directions and also in the vertical direction, and the system without any membrane is shown here. If we have a natural thin clay crust, we can take advantage of it, otherwise we can place a mat of clay soil to isolate the area of treatment from the rest of the soil medium, and once again we connect these vertical PVDs to the drain pipes or the horizontal pipes through which the vacuum is applied. And here in this photograph we can see these horizontal pipelines that are laid on the ground surface, and here we can see the bentonite filled trench all around the treated area. And now let me illustrate how the removal of the atmospheric pressure from the soil increases the effective stresses. Let us take a case where we have the top 3 meters is a sand layer, and then below this we have a clay layer, and let us say that initially the water table is at a depth of 3 meters, and we have installed our vacuum pipelines at a depth of 1 meter below the ground level, and let us assume for the purpose of calculations the dry and saturated unit weights as 17 and 20, I think it should be 18, and then initially the water table is at a depth of 3 meters, and after the application of vacuum pressure, because the atmospheric pressure is removed here, the water table raises up to 1 meter. And so this let us calculate the pressures in the soil before and after the application of the vacuum, and let us calculate the stresses within the sand layer before the application of vacuum. It is the total stress is a PA, that is the atmospheric pressure that is acting on the soil, and then plus gamma dry times Z, and gamma dry is taken as 18. So, it is 100 plus 18 times Z, and the pore pressure is just simply the PA, because that is the neutral pressure that is acting, and the effective stress is sigma V minus U, that is 18 times Z. Is actually we do not normally consider the atmospheric pressure as a pore pressure, but in this case, because we are dealing with the removal of atmospheric pressure, it helps us in separately considering the atmospheric pressure. In fact, this is what we write. Normally, if we have a dry sand, the effective stress is just simply the unit weight multiplied by Z, and let us look at the stresses in the sand layer after the application of vacuum. So, after the vacuum application, the water level will rise from 3 meters to 1 meter below the ground level. So, now the total stress is PA plus gamma dry times 1 plus gamma submerged times Z minus 1, that is the Z is measured from the ground level and 1 meter is the depth up to which the water level rises. So, it is 98 plus 20 times Z, and the pore pressure is Z minus 1 times gamma W. After the removal of the atmospheric pressure, there is no PA. So, it is Z minus 1 times 10, that is the gamma of water, and so the effective stress is 108 plus 10 times Z. So, the increase in the effective stress in the sand layer is the difference between the two pressures 108 plus 10 Z minus 18 Z. So, it is 108 minus 8 times Z. So, that means that at a depth of 1 meter the change in the effective stress is 100 kPa, that is our the atmospheric pressure, and then it is 84 kPa at 3 meters depth. Just for illustration purpose I have taken the PA as 100, but to be very precise the PA is about 101.6. And let us look at the stresses within the clay layer below the water table, and before the vacuum application the total stress is PA plus 3 times 18 plus 20 times Z, and here the Z is measured from the top of the clay surface, and the pore pressure is PA plus 10 Z, and so our effective stress is sigma V minus U, this minus this. So, it is 54 plus 10 times Z, and the stresses in the clay layer after vacuum application is the total stress is PA plus 18 plus 2 times 20, because 18 is because the top 1 meter of sand is unsaturated or without water, and 2 times 20 plus 20 times Z, that is the unit weight of 2 meters of sand, and this is the unit weight of clay soil times Z, that is PA plus 58 plus 20 Z. So, the increase in the effective stress is the effective stress after the vacuum application minus the effective stress before the vacuum application. It comes out as 84 kPa, and this is independent of the Z, and so that is the main advantage that we have with vacuum consolidation, because if you apply surcharge gradually because of the stress dispersion, the effect of the surcharge is maximum at the ground surface, and as you go down below it reduces, whereas here we see that the effect of vacuum is constant with the depth, and I will briefly outline some of the advantages that we have seen. The increase in the effective stress is isotropic and it is constant with depth, and the type of lateral strains that we induce are compressive with vacuum, whereas with normal surcharge there is an outward movement, and there is no increase in the shear stress. So, that means that the lateral ground movements will not take place, and the vacuum consolidation is known to result in more uniform surface settlements, and we do not have to apply any external surcharge pressure to drive the consolidation, and because the increase in the effective stress, immediate increase in the effective stress within the blanket, that acts like a rigid mat for our construction purposes, and the vacuum consolidation is known to get rid of even the secondary consolidation settlements, and some of the field applications of the vacuum methods are listed here. Most of the applications are in Southeast Asia and in Netherlands, where they have extremely soft clays. You see here this is in China, this is in China, this is in Japan, China, Korea, China, and the vacuum consolidation is applied for different field cases, for construction of roadways and airport runways, and then embankments and so on, oil storage tanks. And I will just briefly present some of the results that we have obtained at IIT Madras from studies on vacuum treatment, and just to summarize, I will show you some results. The gain in the shear strength because of the vacuum treatment can be explained easily using critical state soil mechanics theories, that is given here. The experimentally measured undrained shear strength after vacuum applications are given in this column, and those predicted from critical state theory are given in this column. So, that means that we can theoretically estimate the effect of vacuum consolidation, and here we see the application of vacuum, the result of that vacuum on stone column. If we draw the pressure settlement graph, this is the response of the soft clay soil, and this is the response of the stone column that is not treated with vacuum, and the same stone column after the vacuum treatment, it behaves very stiff and also much stronger. That is the main advantage of the vacuum treatment, because it can increase the strength. And here is actually this is some test data comparing the vacuum treatment with surcharge loading, and in both cases a tank was treated by surcharge loading or vacuum treatment, and with vacuum treatment the water content was found to be constant with the depth, whereas with surcharge loading the top the water content is reduced from initial water content of 48% to about 42%, whereas at the middle and bottom the water content is relatively high of 45%, whereas with the vacuum treatment the water content is constant with the depth about 39%. So, that means that the effect of vacuum is relatively constant with the depth, whereas the effect of surcharge is more at the ground surface, and as we go down the depth it is reducing. And here we see the effect of surcharge treatment and vacuum treatment on the response of a stone column. It is the surcharge treated stone column is relatively soft, and it has a lower bearing pressure as compared to that treated with vacuum. So, just to summarize, the introduction of the geosynthetics into the civil engineering field has completely changed the way we do the accelerated consolidation, and this particular lecture has highlighted some of these techniques. Thank you very much.